A powerful earthquake has once again drawn the world's attention to one of the most active tectonic regions on Earth. Offshore southern Mexico, along the Pacific coast near Puerto Madero, a major magnitude 7.3 earthquake struck at 14 minutes before 3 in the afternoon Coordinated Universal Time on July 17, 2026. The earthquake occurred approximately 36 miles, or about 58 kilometers, west-southwest of Puerto Madero, at a shallow depth of approximately 12 miles, or about 18.6 kilometers. Within minutes, seismic monitoring centers around the globe began recording a rapid sequence of aftershocks, including a magnitude 6.0 event occurring roughly 56 miles, or about 90 kilometers, southwest of Puerto Madero, accompanied by dozens of additional earthquakes exceeding magnitude 5. The sequence immediately confirmed that this was not an isolated tremor, but the release of enormous tectonic stress from one of the most dangerous plate boundaries in the Americas. Across Mexico, emergency agencies began assessing coastal communities, while scientists analyzed seismic waveforms, satellite observations, and fault mechanics. Yet as the data accumulated, another topic quietly entered scientific discussions. Researchers who study the western margin of North America once again found themselves answering a familiar question from the public. Whenever a great earthquake strikes Mexico, many people begin wondering whether California might somehow be next. That question is understandable because Mexico and California occupy neighboring sections of the same immense tectonic system extending from Central America through western North America. They share the influence of the Pacific Plate, the North American Plate, and a network of interconnected tectonic boundaries stretching thousands of miles across the eastern Pacific. Images of fault lines crossing maps often create the impression that one large earthquake simply marches northward toward California. Reality is considerably more complex. The earthquake that struck offshore southern Mexico originated within a tectonic environment entirely different from the famous San Andreas Fault. Although both regions experienced destructive earthquakes, they are driven by different geological processes, operating on different kinds of plate boundaries. Understanding those differences is essential for separating scientific evidence from speculation. The epicenter lay offshore in the Pacific Ocean near the Middle America Trench, one of the most active convergent plate boundaries anywhere on Earth. This submarine trench marks the place where the dense oceanic Cocos Plate moves steadily northeastward before descending beneath the North American Plate. Every year, the Cocos Plate advances approximately 3 inches, or about 76 millimeters, toward the continent. That movement may seem insignificant over a single year, but over decades and centuries it stores extraordinary amounts of elastic energy inside Earth's crust. Unlike plates that slide smoothly past each other, converging plates often become locked together. Friction prevents continuous motion while the tectonic plates continue trying to move. Rocks slowly bend, compress, and accumulate stress. Eventually, the resistance becomes greater than the rocks can withstand. When that threshold is exceeded, the fault suddenly slips, releasing energy accumulated over many decades in only a matter of seconds. That is precisely the mechanism responsible for the magnitude 7.3 earthquake. Seismic analyses indicate the earthquake resulted from reverse faulting, commonly called thrust faulting. Instead of one side sliding horizontally past the other, the overriding plate was forced upward as the subducting plate continued pushing beneath it. This style of faulting is characteristic of major subduction zones around the world, including those responsible for some of history's largest earthquakes. Because the rupture occurred at relatively shallow depth, seismic waves reached nearby coastal regions with considerable intensity. Shallow earthquakes generally transmit stronger shaking to the surface than deeper earthquakes of comparable magnitude because less energy is absorbed while traveling through Earth's interior. Within approximately 30 minutes, a significant magnitude 6.0 aftershock struck southwest of the main rupture. Numerous additional earthquakes exceeding magnitude 5 continued rattling the offshore region. Such aftershock sequences are expected following earthquakes of this size because the surrounding crust must adjust to the redistribution of stress produced by the initial rupture. Although aftershocks can continue for weeks, months, or even years, their frequency usually decreases over time according to well-established statistical relationships observed worldwide. Nevertheless, some aftershocks become damaging events in their own right, especially if weakened buildings have already sustained structural damage during the primary earthquake. Southern Mexico has experienced this pattern repeatedly throughout recorded history. The geological foundation of this region explains why. Mexico occupies one of the most tectonically complicated locations anywhere on the planet. Instead of sitting quietly upon a single stable plate interior, the country lies where several major and minor tectonic plates interact simultaneously. The North American plate dominates much of the continent, while the Pacific plate influences the western margin. South of Mexico lies the Cocos Plate, accompanied farther west by the Rivera Plate, and to the southeast by the Caribbean Plate. These interacting plates create multiple styles of deformation across relatively short distances. Along Baja California, transform faulting dominates as plates slide horizontally. Farther south, near the Gulf of California, seafloor spreading contributes to crustal extension. Along southern Mexico, however, subduction becomes the defining geological process. The Middle America Trench extends for approximately 1,700 miles, or about 2,700 kilometers, from western Mexico toward Costa Rica. This deep ocean trench marks the surface expression of the descending Cocos Plate as it sinks into Earth's mantle. Oceanic lithosphere is denser than continental crust because it consists primarily of basalt and gabbro rather than lighter granitic rocks. As oceanic crust ages, it cools, thickens, and becomes even denser. Eventually, gravity assists its descent beneath adjacent continental plates. This continuous sinking process recycles enormous sections of Earth's crust back into the mantle. Yet subduction does far more than recycle rocks. It builds mountains. It generates volcanoes. It creates devastating earthquakes. It produces tsunamis. Few geological environments combine so many powerful processes within a single region. As the Cocos Plate descends beneath southern Mexico, increasing temperature and pressure release water trapped inside hydrated oceanic minerals. These fluids migrate upward into the overlying mantle wedge, lowering the melting temperature of surrounding rocks. Partial melting begins, generating magma that slowly rises toward the surface. Over millions of years, repeated volcanic activity has produced the Trans-Mexican Volcanic Belt stretching across central Mexico. Famous volcanoes owe their existence to the same tectonic engine responsible for offshore earthquakes. Thus, earthquakes and volcanoes are different expressions of the same long-term geological system. The earthquake itself occurred along the interface where the descending and overriding plates remain locked together. Scientists refer to this as the megathrust interface. These faults are capable of generating the largest earthquakes known on Earth because rupture surfaces may extend hundreds of miles beneath the ocean floor. Historical records demonstrate that southern Mexico has repeatedly produced destructive subduction earthquakes. Large earthquakes occurred during the 19th century, throughout the 20th century, and into the 21st century. Some generated destructive tsunamis, others caused widespread structural damage across coastal communities. Several exceeded magnitude 8. Each event released stress from one section of the plate boundary while neighboring segments continued accumulating strain. This patchwork behavior explains why seismic hazard persists despite previous earthquakes. A fault does not become permanently safe simply because it ruptured once. Stress continues accumulating as tectonic plates never stop moving. Modern satellite measurements using global positioning system networks clearly reveal this ongoing motion. Stations distributed throughout southern Mexico measure crustal movement with remarkable precision, documenting slow deformation as the overriding plate is gradually compressed by the advancing Cocos Plate. Although annual movement measures only a few inches, centuries of uninterrupted convergence accumulate tremendous displacement. Eventually, nature balances the equation. The magnitude 7.3 earthquake represents one installment within that endless geological cycle. Its focal mechanism strongly supports thrust faulting directly associated with plate convergence. Seismologists determine focal mechanisms by analyzing the first arriving seismic waves recorded at stations worldwide. Compression and extension patterns reveal the orientation of fault movement even when the rupture occurs deep beneath the ocean. In this case, The mechanism clearly indicated reverse motion consistent with subduction zone rupture rather than strike-slip faulting. That distinction becomes extremely important when discussions shift toward California. California's most famous fault, the San Andreas Fault, belongs to an entirely different tectonic category. Instead of one plate diving beneath another, California's dominant tectonic boundary is largely transform in nature. There, the Pacific Plate slides northwest relative to the North American Plate. Movement occurs primarily horizontally rather than vertically. Imagine placing two thick books side by side. Sliding one beneath the other resembles southern Mexico. Sliding them sideways resembles California. Both motions generate earthquakes, yet the underlying mechanics differ significantly. The San Andreas Fault extends approximately 800 miles, or about 1,300 kilometers, through California. Rather than forming a single fracture, it consists of numerous interconnected segments exhibiting different behaviors. Some portions creep slowly without producing major earthquakes. Others remain locked for centuries before rupturing catastrophically. California also contains dozens of additional active faults, including the Hayward Fault, San Jacinto Fault, Elsinore Fault, Calaveras Fault, Garlock Fault, and many offshore fault systems. Each possesses its own earthquake history and stress evolution. Therefore, scientists evaluate California's hazard primarily according to stress already accumulating within California, rather than earthquakes occurring thousands of miles away. Why, then, do experts continue watching California whenever a large Mexican earthquake occurs? The answer lies not in immediate earthquake prediction, but in broader tectonic awareness. Large earthquakes produce permanent stress changes surrounding the rupture area. Some neighboring faults experience increased stress while others experience slight reductions. These changes strongly influence aftershock locations and occasionally trigger nearby earthquakes. However, these stress transfers diminish rapidly with distance. By the time one reaches California, the direct stress change from a southern Mexican earthquake becomes extraordinarily small. Extensive scientific research over several decades indicates that large earthquakes generally do not trigger major earthquakes thousands of miles away through permanent stress transfer alone. Instead, California remains under observation because it is always under observation. Every significant earthquake anywhere along the Pacific margin encourages scientists to compare rupture characteristics, evaluate seismic monitoring systems, and reassess regional preparedness. Researchers examine whether the event reveals new insights into rupture propagation, ground motion, tsunami generation, or subduction mechanics that may improve hazard assessments elsewhere. Temporary dynamic stresses generated by passing seismic waves can occasionally trigger tiny earthquakes in geothermal fields or already unstable fault zones far from the original rupture. These events are generally small and do not establish that one major earthquake directly causes another distant major earthquake. Consequently, responsible scientific interpretation requires careful distinction between coincidence and causation. California's earthquake probability remains governed primarily by its own tectonic conditions. Southern Mexico's earthquake resulted from long-term convergence along the Middle America Trench. The San Andreas system evolves according to decades and centuries of horizontal plate motion between the Pacific and North American plates. Both systems are active simultaneously because plate tectonics never pauses, not because one routinely triggers the other. Still, comparisons between the two regions reveal fascinating similarities. Both accumulate elastic strain over extended periods. Both contain locked fault segments. Both experience earthquake clustering. Both require continuous monitoring using dense seismic networks. Both demonstrate that Earth's crust releases energy irregularly rather than according to predictable schedules. Modern seismic monitoring across North America now operates with unprecedented sophistication. Thousands of broadband seismometers continuously record even the faintest vibrations. Satellite radar detects millimeter-scale surface deformation. Ocean bottom instruments increasingly expand coverage offshore, where many of the largest earthquakes originate. Within minutes of the Mexican earthquake, scientists worldwide had already estimated its magnitude, depth, rupture style, and approximate location. Such rapid analysis represents decades of technological advancement. Even so, earthquake prediction remains beyond current scientific capability. Researchers can estimate long-term probabilities based on geological history, fault slip rates, and accumulated strain. They cannot specify the exact day an individual fault will rupture. That limitation often frustrates the public, especially after large earthquakes generate widespread media attention. Yet uncertainty does not indicate ignorance. It reflects the immense complexity of Earth's crust. Every major earthquake provides another opportunity to refine models describing rupture initiation, fault friction, stress accumulation, and seismic wave propagation. The magnitude 7.3 earthquake offshore southern Mexico will undoubtedly become another valuable dataset within that continuing scientific effort. Geologists will compare satellite observations before and after the earthquake to measure permanent crustal displacement. Marine geophysicists may examine whether sections of the seafloor experienced uplift or subsidence. Seismologists will relocate thousands of aftershocks to reconstruct the precise geometry of the ruptured fault. Numerical simulations will estimate stress redistribution throughout adjacent portions of the subduction interface. Each analysis contributes another piece to understanding one of Earth's most powerful tectonic environments. Meanwhile, communities along the Pacific coast continue living beside an active plate boundary that has shaped landscapes for millions of years. Mountain ranges owe their elevation to tectonic compression. Volcanoes owe their existence to descending oceanic crust. Earthquakes reflect the continuing adjustment between converging plates. Far from representing isolated disasters, these events reveal an active planet continually reshaping its surface through forces operating deep within the lithosphere. The July 17th earthquake serves as another reminder that Earth's largest geological processes unfold continuously whether humans notice them or not. For countless generations, the Cocos Plate has advanced relentlessly toward the North American plate. It moved before recorded history. It moves today. It will continue moving long after present generations have passed. Every few decades or centuries, accumulated strain reaches failure. When it does, earthquakes like the magnitude 7.3 event remind humanity that continental margins remain dynamic boundaries rather than permanent fixtures. Scientists will continue closely monitoring southern Mexico as aftershocks gradually decrease. They will continue monitoring California because it possesses its own significant earthquake hazard independent of events farther south. Most importantly, they will continue improving understanding of plate tectonics through careful analysis rather than speculation. Each new earthquake expands scientific knowledge while reinforcing an enduring lesson written across Earth's geological record. Tectonic plates never sleep. They advance inch by inch, year after year, silently storing energy across immense fault systems hidden beneath mountains and oceans alike. Eventually, that energy is released in moments powerful enough to reshape coastlines, alter landscapes, and remind civilization that the forces building continents remain very much alive. The magnitude 7.3 earthquake offshore southern Mexico stands as another chapter in that ongoing process, one that commands respect, careful scientific study, and continued preparedness across the entire Pacific margin, from the shores of Mexico to the fault networks of California.